Hey everybody, welcome back to Chapter 7 where we're going to continue our discussion about probability, and this time we're going to apply it to different distributions and figuring out probabilities like we did before when we were talking about the normal distribution or the standard normal distribution. So let's dive in. Before that, a little bit of review. What is the probability of pulling a black card or a king out of a 52 card playing deck? So this is just one single choosing of one card out of a 52 card playing deck. The answer is 0.54, so it's going to be D. How do we figure that out? Well, we use the addition rule that we learned last time, where if you have a probability of an or, one thing or the other in one single event, you can use the addition rule. And so what we end up with is the probability of pulling a black card, which is 0.50. There's half of them are clubs or spades, so 0.50, plus the probability of obtaining a king, 4 kings out of the 52 playing card deck, so it's 0.077, and then we subtract the probability of getting a king that is also a black card, so a club or a spade. Well, there's only 2 of those, so that's 2 out of 52, which is a probability of 0.039. If you go through all the math, you get a combined probability of 0.538, which we round to 0.54. So what we're talking about today is a specific kind of distribution called the binomial distribution. Bi meaning 2 and nomial meaning numbers. Okay, so what happens in a binomial distribution is if there are only 2 possible outcomes of a particular event. So a good example of this is flipping a coin, right? Just a normal, let's say a quarter. It's got one head and one tail, right? And so there's only 2 options. You either have a head or a tail, and those things are mutually exclusive. So when we describe probability of a binomial distribution or a binomial event, we use P and Q, right? P means the probability of basically what you consider to be a success. And in this case, we'll take it to be the probability of the head, right? Getting a heads. Whereas Q means the probability of not getting that, of basically failing, of getting the opposite. And so in this case, Q would be the probability of a tail. Now in this particular case, right, the probability of a head is 0.5. It's 1 out of 2, and the probability of getting a tail would be 1 minus 0.5 essentially, which is also 0.5 because again, there's one tail out of 2 sides. So you get a probability for each of these as 0.5. So let's say we were interested in if we were to flip a coin 10 times. Well, what would be the probability of different numbers of successes out of those 10 coins? And here a success is defined as getting a certain number of heads out of those 10 flips. So what you can see here is because the probability of getting a heads is the same as getting a probability of getting a tails, what's nice is this creates a symmetrical binomial distribution where you can see that different possible numbers of successes, again, the number of times you get heads out of 10 coin flips, is symmetrical, and it increases up to a value of 5 coin flips being heads and then decreases again. So what this is saying is if you look at the x-axis, number of successes, that's the number of heads out of 10 coin flips. Y-axis is the probability of that event or of that success rate happening. And so if you flip 10 coins and you want to know, well, what's the probability that I will get exactly 2 of the 10 coin flips to be heads? 2 of those 10 coin flips come up as heads. And you can see here it's a little below 0.05. Okay, which means it's a little bit below 5% chance of getting exactly 2 heads out of 10 coin flips. The probability of getting exactly 5 heads out of 10 coin flips is getting close to 25%, 0.25. That's the middle bar, right? Well, it makes sense that getting a very low number of heads or getting a very high number of heads is particularly unlikely, given that the probability of heads and tails is equivalent. More likely, you're going to get a number of successes kind of in the middle, and so that's why the distribution looks nice and symmetrical. And if you wanted to, you could also ask the question, well, what's the probability of getting, let's say, 7 or more heads out of 10 coin flips? Well, in that case, you would look at the probability for getting 7 heads out of 10, and you would add to that number the probability of getting 8 heads out of 10, and add the probability of getting 9 heads out of 10, and add the probability of getting 10 heads out of 10. So you would add all of those things up, and that would give you the total probability of getting 7 or more heads out of 10. And you can ask, of course, well, how do we calculate that probability? If I flip a coin 10 times and I want to know what the probability is that I'll get heads exactly 5 times out of those 10 coin flips, how would I try to calculate that, go about that? Well, there's this big old equation over here. I mean, it's not too scary, but it's a little scary. And we are not going to worry about this equation. Okay, we're not going to calculate this kind of stuff by hand. Although if you want to, you can look it up on YouTube or whatever if you're interested in finding out how to do that. But where this gets applied is in the case where you're interested in finding out a certain number of successes or more, or a certain number of successes or less than that number of successes out of a certain number of events, then we can start thinking about, well, where have we seen that before? Well, when we calculated z-scores, and then we looked up in the standard normal table or a normal curve table, what's the probability of observing that z-score or more, or that z-score or less? Aha! We can apply the same type of logic to the binomial distribution and get it essentially an answer of, well, how likely is it that I would see 5 heads or more out of 10 coin flips, for instance. And so instead of using that real scary equation on the previous slide, we can find a z-score based on probabilities found in the binomial distribution, and then we can actually approximate something like the normal curve, the standard normal curve. And so we can use z-scores to actually find the probability of obtaining a certain value or more, or a certain value or less on the normal table, or the standard normal curve table, okay? So what we actually want to do is, first of all, recall, well, how do I get a z-score in the first place? Z-score, as you'll see on the bottom left there, is just whatever the raw score is minus the mean. This is the sample mean in this case. If it was the population mean, instead of x bar, it would be mu. You divide x minus x bar by the standard deviation of the sample, s. Or if it was a population, it would be sigma, would be the standard deviation of the population. Okay, so how do we find those values when we're talking about probabilities of one event occurring or another event? That's binomial. So what we have to do is we take x bar, the mean, is actually equal to the number of events, which is essentially the number of scores, the number of people. But now when we're talking about coin flips, it's the number of coin flips, n, times the probability of success, whatever you define success to be as. And in this case, p will equal the probability of obtaining heads. S, the standard deviation, is going to be equal to the square root of the number of events, the number of coin flips, times the probability of success, times the probability of failure, or the probability, in this case, of getting tails. So if we put that all together, then the z-score, when you're thinking about a certain number of successes, is equal to the number of successes minus the number of attempts, the number of events, n, times the probability of success, so x minus n times p, divided by the square root of n times p times q, the number of events times the probability of success times probability of failure, and that thing square rooted, or taken the square root of. Okay, so let's say you flip a coin 80 times. What is the probability that you will obtain 46 or more heads? So first of all, we would find the mean. The mean is the number of events times the probability of success. So that's going to be 80 events. You flip a coin 80 times, multiplied by 0.5. That's the probability of obtaining a heads. And 80 times 0.5 is 40. Okay, good. We've got the mean. Now, how about the standard deviation? Okay, the standard deviation is the square root of n, number of coin flips, which is 80, times p, probability of success, times q, probability of failure. 0.5 times 0.5, because it's the probability of a heads versus the probability of a tail. So you work out that math, you get 4.472. So now we have the mean and standard deviation, and all we have to do is calculate a z-score, and then we can look up in the standard normal table or the normal table, what is the probability of obtaining that z-score or greater. Okay, so I moved the equations and the results for the mean and standard deviation up above, and now we're going to calculate the actual z-score. So we're interested in our x is going to be 46 heads, okay? So we take 46 and we subtract the mean that we just found above, which is 40. 46 minus 40 is going to be 6. And we divide that by the standard deviation, which we found to be 4.472. If you do that math, you end up with a z-score of 1.34. So a z-score of 1.34. And remember, that's in units of what? That's in units of standard deviation. So that means that getting 46 heads is more than the average, right? You'd probably think that the average would be what? 40, right? Because it's a 0.5 chance that you, so we already found the average. The mean would be, you'd think you'd get 40 heads if you were to actually flip a coin 80 times. So if we were thinking about trying to get 46 heads, that's going to be above the mean. And so any scores that are above the mean are going to result in positive z-scores that are above a z-score of 0. So in this case, we have a z-score of 1.35. So that means getting 46 heads is going to put us at 1.34 standard deviations above the mean. And we can ask, okay, well, what's the likelihood of getting 1.34 standard deviations or more above the mean? 46 or more heads out of 80. Okay, so you go to the back of your book, or you find a z-table online, or a normal table, standard normal curve table online or something like that. And what you see is, if you find the z-score that we just calculated of 1.34, well, you're going to go all the way over to the smaller portion, because just like the diagram on the right, the distribution on the right there, we're looking for what is at or above a z-score of 1.34, and since 1.34 is already on the right side of the mean, then we're going to be looking for the smaller portion, which is to the right. Okay, so we end up with what? A probability of 0.0901. And that means that there's about a 9% chance, you move the decimals twice if you're multiplying it by 100 to get the actual percentage chance, 9.01% chance of obtaining 46 or more heads out of 80. Now, if I had asked you, what's the probability of getting 46 or less heads out of 80 coin flips? Then you'd be looking at the larger portion, okay? And so that would be 0.9099. That's 90 0.99% that you would get 46 or less heads out of 80. But the two outcomes don't necessarily have to have the exact same probability of happening. So a good example of this would be if you're comparing people in a crowd who are left-handed to people who are right-handed. Well, in the normal population, the probability of people being left-handed, about 10% of people are left-handed and 90% of people are right-handed. And you'll notice again, the probabilities have to add up to 1, right? Because you want two outcomes that are mutually exclusive, and the probability of both of them combined is going to add up to 100%. So the probability of being left-handed is 0.1, and the probability of being right-handed is 0.9. And I'm sure a bunch of you are like, well, what about ambidextrous people? Let's just pretend that being left-handed and being right-handed are the only options, even though obviously that's not necessarily the case. Now we've got a bit of a problem, okay? So the binomial distribution is not symmetrical or normally distributed if you have probabilities that are not equivalent between success and failure. Okay, so we've got a probability of 0.1 for left-handed people and a probability of 0.9 for right-handed people. So the distribution is going to be skewed. Okay, it's going to be a little skiddly-wampus. And in this case, it's skewed right because you'll get very few people are going to be left-handed. And so the number of successes in this case out of 10 people, you're going to have way more zeros and ones and twos in terms of amount of left-handed people out of 10 than very high amounts of left-handed people out of 10, just because the chances are less that you're going to have left-handed people at all, right? So that's a bit of a problem, because if the distribution is skewed, then we can't use the normal distribution, the standard normal distribution, to think about, well, what are the percent chances that you would get, X amount of left-handed people out of X amount of people? Well, the nice thing about the binomial distribution, though, is that as the number of events increases, so in this case it'd be the number of people. If it was coin flips, the events is the number of coin flips. As that increases, you start to approximate a normal distribution. So for instance, this is the binomial distribution for a probability of 0.1, like we saw with left-handed people, 10%, but now there's 150 people instead of 10 people. And you can see that the curve is still very slightly right skewed, but overall it looks fairly normal, right? It's a fairly normal distribution, fairly symmetrical, and that's what we want, so that we can actually calculate z-scores and be fairly certain that they're going to match pretty well with the actual normal distribution, which is made of z-scores also, but it's not skewed at all. It's perfectly symmetrical and normally distributed. So we're going to basically fudge the numbers a little bit and just go for an example that has a large number of people in this particular binomial distribution, and then we don't really have to worry about that issue very much. All right, so let's do the example. There's going to be 150 people in a room. Now, what's the probability that 20 or more of those people are left-handed? So again, we need to calculate the mean and standard deviation. Could actually be argued, if there's a group of 150 people and you get all 150 people, then that could be the population, right? So we might actually use mu instead of x bar and sigma instead of s to represent that. But anyways, let's pretend it's a sample of 150 people out of some larger population. So to calculate x bar, again, that's the number of events, or in this case, the number of people, times p, the probability of success. And we're defining success as people who are left-handed. So 150 times 0.10 is going to be 15. That's the mean. Standard deviation is going to be the square root of number of events times p times q. 150 times 10% chance of being left-handed, 90% chance of being right-handed. You do the math there, you get 3.674. That's going to be your standard deviation. Now, in order to calculate the z-score, we subtract our mean of 15 from the raw score that we're interested in, the number of successes that we're interested in, which in this case is 20. 20 minus 15, of course, is going to be 5. And we divide that by our standard deviation of 3.674. And if you do that math, you get a z-score of 1.36. 1.36 standard deviations above the mean. So then, of course, we've got our z-score, and we can go over to our normal distribution table, and we look up a z-score 1.36, and since it's 1.36 or more, because we're looking at 20 people or more being left-handed, then you go again to the smaller portion. Okay, so that's going to be 0.0869, or 8.69%. likelihood that you would see 20 or more left-handed people in a group of 150. And of course, if I was interested in what's the probability of 20 or less of them being left-handed, then you use the larger portion, that's 0.9131. Here's a trickier though, much trickier. Let's say I'm only interested in what are the chances that only one of the people is left-handed out of 150. And let's just say, I'm not doing the calculations, but let's just say I get a z-score that's negative. I get a z-score that's negative, and let's say it's negative 1.36 instead of positive 1.36. Again, I'm just making these numbers up, but imagine you get a z-score of negative 1.36, and I'm interested in what's the percent likelihood, or what's the probability that you will see that many people or more. Well, if it's a negative z-score, then you actually are looking at the larger portion, because negative z-scores are below the mean. So the larger portion is going to be above them. Hopefully that makes sense. Whereas if I want to know, well, what's the likelihood of obtaining, again, let's just say one left-handed person out of 150, and it's negative 1.36, which it probably will not be, but negative 1.36 is the z-score. And I want to know, well, what's the percent likelihood that it would be that or less? Then I'm going to look at the smaller portion, because it's going to be a tiny part of the tail at the left end of the distribution. So you have to kind of flip-flop the larger portion and smaller portion depending on if you're using positive z-values or negative z-values. All right, that's it for this one. Hope you have a great day, and I will see you in the next video.